Okay, I think we should start. So, welcome to the first colloquium of the winter quarter, 2020. In this first colloquium, we have Professor Amir Yacobi from Harvard University. He's the first HANA visiting professor of 2020. This program of the HANA visiting professorship was established by the family of Stan Hana, who was a member of the Department of Physics from 1963 until he retired in 1991, but then still was around for quite a few years later. The goal of in his honor, it was established by his family. The goal was to bring eminent scholars to Stanford for an extended period. Amir Yacobi certainly fits this bill, and he's going to be here for exactly 1 month. So it was, he just arrived yesterday, and will stay for a month. So if you get excited by what he says, you want to talk to him, he is sitting in the 3rd floor of McCullough, and his door is open every day. Amir is a professor of physics and applied physics at Harvard. He did his actually BS in aeronautic engineering, then moved to physics and did his PhD at the Weizmann Institute. From Weizmann in '94, he went to Bell Labs as a postdoctoral fellow, and then became a member of the technical staff there, after which he moved back to the Weizmann Institute as an assistant professor, then associate professor, and then was grabbed by Harvard in 2006. And he's there since as a professor of, as I said, physics and applied physics. He won many awards, starting early on with the Macmillan Award in '98. He holds a Kavli Chair at Technical University of Delft, the AAA Newcomb Cleveland Prize of 2006. He's a member of the National Academy of Science and a fellow of the American Physical Society and of AAAS. He made seminal contributions to condensed matter physics, especially to understanding coherence in quantum mesoscopic systems, developed techniques to probe electronic systems, techniques that are at the cutting edge of condensed matter physics. Imaging techniques such as the single electron transistor, scanning single electron transistor, and his current interest is understanding behavior of low-dimensional systems, with applications to quantum information science. And I think that this talk today will touch on some of the interesting things that Amir is doing in his lab. So, welcome.
I have to say I'm really disappointed by this introduction. I really was counting on Aaron to embarrass me much more, but nonetheless, thank you for this kind introduction.
Nice guy.
Yes. So, I'd like to start by thanking Aaron, the two Steves who can't be here today, for inviting me, giving me this opportunity to spend time at Stanford. I'm really looking forward to my stay. And I want to kind of echo what Aaron was saying. Please do come and talk to me. That's the whole purpose of spending here an extended period. Today I'd like to tell you about some of the recent work we've been doing to explore new ways of looking into condensed matter phenomenon. And I'd like to start by motivating this a little bit, giving you some idea of why I believe that developing new approaches for looking at materials, at various phenomena is really important. After all, we do have quite phenomenal techniques already in our toolbox, so why do we need more? So I'm going to give a handful of examples. This is by no means any exhaustive list, just to give you a sense of why, where are the limits of some of the things that one might be interested in. Here people are very familiar with topological insulators. This is a two-dimensional topological insulator where the center layer here is an insulator in the bulk, and yet it supports edge modes that live on the boundaries. And as you can see from this sketch, the boundaries support counterpropagating edge states, one carrying spin of one kind, and the other counterpropagating edge is carrying the spin of the opposite sign. So obviously there is no net current flowing along the edge. But as you can see, there's a net spin current. And this spin current is flowing in equilibrium in this material. And currently, there aren't really any methods that I'm familiar with that could probe the presence of a spin current in this material. So how do we verify this idea that this thing really in its ground state is supporting a spin current? Layered materials is yet another area of explosion recently in condensed matter. When you take graphene sheets, you put them one on top of the other with a slight angle, the system can develop various insulating states. And here I'm just showing one theory plot from a recent theory paper that suggests the underlying physics behind this insulating state. And what you can see is that on the atomic scale inside this material, there are currents that are flowing clockwise, counterclockwise, and no current. And the challenge here is that the size scale in which these currents are flowing are atomic. And again, it's really hard to have a technique that would allow you a spatial resolution that would unravel the presence of this circulating currents. Another example is the graphene sheet here, some experiments we've done in the past. When it's subject to a strong magnetic field, it turns out that it can enter an antiferromagnetic state. And you might say, well, we know how to probe antiferromagnetism. There are a variety of tools, scattering techniques, for example, that allow us to probe antiferromagnetism. The challenge here is that the volume of material that we have is extremely tiny. This is only one monolayer. The lateral scale is of order a few microns. And furthermore, the electron density, the density of these dipoles is about 1 million times smaller than what you'd find in a conventional antiferromagnet. So just quantity-wise, signal-wise, this material will not be suitable to conventional exploration. And again, the question is, how do we test these notions, some of the predictions that exist for these materials, that indeed there is an underlying antiferromagnetic state in this system? So these examples are just, again, a handful of examples in a ground state of some modern condensed matter problems. We can go one step beyond the ground state and look at excitations. So here again, I just point out two examples. One are spin liquids. These are materials that are highly frustrated, magnetic materials, highly frustrated, where in the ground state, the various electrons that are localized to atomic sites want to form singlets. And in fact, the ground state is believed to be a quantum coherent superposition of all possible singlets that can exist in this material. So this is a very highly correlated ground state. But here I want to talk about the excitations. It turns out that in this material, there are excitations that carry spin but no charge. These materials are typically insulating. The spin excitations are fermionic, unlike some of the spin excitations I'll talk later in the talk, which are bosonic. So they have heat that it conducts heat very similar to metals, even though there is no charge that is associated with any of these excitations. So again, it would be nice to have techniques that could sense spin excitations where charge is completely absent in this material. Another example are different type of topological materials called topological superconductors. These can support excitations known as Majoranas. They have quantum statistics that defies conventional particle statistics that we're familiar with, fermionic or bosonic. They're non-abelian. When you exchange two of these particles, you get a new quantum state. And again, we're lacking techniques to image and to test the presence of these non-abelian excitations. Beyond the presence of excitations, one can ask, well, if these excitations are actually long-lived, you can talk about the transport of excitations. Here, for example, are a set of problems that I'll talk about a little bit later, where a material, rather conventional magnet, can support in principle, this is theory again, superfluidity of spin. So this means that you can basically flow spin in this material in a nearly dissipationless manner. The reason I'm saying nearly as opposed to real dissipationless as you find in superconductors is because spin is not a conserved quantity. It can lose its angular momentum to a lattice. However, these superfluids can indeed support spin currents over very long distances, very different from a thermal propagation of spin excitations. And I mentioned spin liquids before. Spin liquids under certain conditions will also support quantized heat currents. So here again, developing techniques that allow us to probe heat propagation or spin propagation are all kind of very desirable. So this is just a handful of problems that I'm very interested in, and we really lack methods of exploring them. And so over the past decade or so, we really set out to develop new ways of approaching some of these challenges. And I'd like to tell you about one category of problems and solutions that we found over the past several years. So what I'm hoping to do is to show that a spin quantum bit, and I'll describe exactly what that is, can provide information both on ground state properties, mesoscopic sample dimensions, explore underlying excitations, and transport. Again, it's not a solution for everything, but it definitely provides some insight into certain problems that we're interested in. And I'd like to encourage, especially the students here, to continue thinking about these problems, to figure out new ways of probing materials, because every time, for me, this kind of approach has been very rewarding. Every time you find a new way of looking into a material, you discover surprises that come along with it. So this is going to be the outline of my talk. I'm going to talk about 4 different topics today from kind of a 10,000-foot, from very high above. And what I'd like to highlight is that despite the fact that this is only one sensor, there is basically one quantum degree of freedom that is going to be used to probe many different phenomena, I'm going to highlight the connection. How is it? What is the connection between the quantity that we're actually measuring and the quantities that are of interest? This is really the key in instrumentation development, is that there is kind of complicated physics that connects quantity that you measure with the quantity that you want to measure. And the topics that I'll cover are analogs to magnetic resonance imaging, where here we'll be looking, the quantities of interest are density and location of paramagnetic spins. I'll talk about magnetization. What is the connection between magnetization and magnetic field? We're going to talk about spin excitations. These are going to be bosonic excitations, and what their connection is and the chemical potential of these spin excitations to the quantities that we know how to measure. And lastly, hydrodynamic electron flow. Here, what's generating magnetic fields are the orbital motion of electrons, namely the charges themselves, while they're moving, are generating magnetic fields. I know there have been several talks about NV centers here, so I'm not going to spend a lot of time describing what an NV center is, just essentially one slide. It's a defect in diamond that consists of a nitrogen substitution and a missing carbon atom. Its level, it basically is an atomic scale defect, and it has a very simple level diagram, 3-level system. It's a triplet. The ground state is insensitive to magnetic field, and the 2 excited states depend their energies oppositely to a magnetic field, with a slope here, the G factor, which is very well known. The way we probe this sensor is by shining light. You shine some green light on it, it fluoresces in the red. By collecting light, you can determine whether this defect is in its ground state or one of its excited states. The intensity of fluorescence is different for the ground state and the excited state. And illuminating the system also helps us initialize the system into its ground state. So it's very convenient, and I'll mention a few more of its properties in just a bit. It's diamond, so its properties are unchanged over a very, very broad range of temperatures. And lastly, because the size of this defect is atomic, in principle, it provides a way of measuring quantities almost with atomic resolution. And I'll talk about spatial resolution because spatial resolution is something that depends on on the problem that you're actually exploring. It's not something that's fundamental to a particular setup. All right, so this defect is basically a two-level system. It's a two-level system if you just choose two of these levels rather than a zero magnetic field. You have three. At any finite magnetic field, you can isolate two of these systems. So it's a two-level system. And what makes it a very, very versatile tool is the fact that you can initialize it. As I mentioned, just shining light prepares it in its ground state. You can control it basically by sending some RF signals. You can point this spinner on the three-dimensional block sphere at any position that you desire. And finally, you have a way of detecting which spin state it is by, again, shining light, recording some red photons from the system. And it's these three ingredients that makes this into a really very versatile quantum sensor. So I'd like to give a sense of how would we use this as a magnetic sensor. So we'll initialize along the North Pole, let's say the ground state, and then we'll tilt it onto the perimeter here, equator, to form a superposition of 0 plus 1. We'll then subject this defect to an unknown field, a magnetic field whose magnitude we don't know. And this is going to cause a precession. And the precession here is going to acquire a phase. And the question is, what is the maximum phase that we can acquire? So of course, if we're able to evolve this defect for a time t, then the phase is going to be the external field that we don't know times this time t. And of course, the limiting time here is its coherence. If it loses information, it interacts with its environment, then we're stuck. And so the maximum time here is going to be the coherence of this defect. Now, we'd like to compare the signal to the noise. Now, this is a quantum sensor. Every time you probe it, there is a lot of uncertainty. And in fact, the maximum uncertainty, if you had a single shot readout, would be pi. You wouldn't really know what the phase is. But you can improve upon it by repeated measurements, and you're going to improve by the basic standard limit of how you cancel errors. And so it's going to improve by the square root of the number of measurements. And when you compare, therefore, the signal to the noise, you can arrive at a condition for what the sensitivity is, and you see that it improves with longer coherence time and longer repetitions, higher number of repetitions. And if I just plug in some numbers, a typical coherence of this defect is about 100 microseconds. It's not that long, only 100 microseconds. The magnetic field sensitivity is about 10 nanotesla. Just to give you a scale, if you take a single electron and you ask what is the magnetic field generated by this electron at a distance of about 10 nanometers from the electron, that field is about 1 microtesla. So 10 nanotesla is a pretty small magnetic field, and we'll see that it basically opens up a lot of possibilities for us. Now, so far I've described how to measure a DC magnetic field. Really, the power of this technique and the reason it can approach so many different problems is the fact that you can also measure non-static magnetic fields. So here, the first three steps are precisely what I described before. We initialize, we tilt, and we let evolve. But now, after some time, we can flip this spin on the Bloch sphere in such a way that if the magnetic field was constant throughout this entire period, we will undo the phase that we acquired. So this sequence now becomes insensitive to DC magnetic fields, but in fact, if we have an alternating magnetic field whose frequency precisely fits within the sequence, it becomes a very sensitive probe to that frequency. Because if the sign of magnetic field also changes after our pi pulse, the phase is going to continue to increase. So the key point is that depending on the type of pulse sequences that we apply to this probe, we can design filters in frequency space that allow us to extract any portion of a magnetic field signal all the way from DC to relatively high magnetic fields on the order of several gigahertz, and we can really peel off many different sections of this spectrum by choosing correctly the way we control our sensor. Over the years, we've really kind of developed highly sophisticated fabrication techniques in order to be able to use this as a scanning probe. What you see here is a slab of diamond that is one monolithic piece of diamond. It started out as a chunk and went through a lot of steps of fabrication to produce this pillar that serves as a waveguide to guide the light out, which is emanating from the tip here, where you have one defect, one NV center sitting roughly 10 nanometers from the surface. Over the past more recent years, we've really switched from these very thin probes to much thicker probes. This has reduced the number of fabrication steps that we need considerably, and makes these probes even more robust than they were before. And we now have really kind of very precise control of the taper of these pillars, the angle of these pillars, which optimize the guiding of light generated at the tip in the direction of our collection system. And recently, since we need to control this defect using microwave signals, we are beginning to incorporate onto the tips themselves the RF antennas that drive the magnetic fields needed to drive our defect. So we're really kind of pushing in the direction. And I think since our work on this, there are actually two companies now that are selling both probes, tips of this kind, and I believe that one of them is beginning to even sell a complete solution, an atomic force microscope for NV microscopy starting this March. I think they're going to announce it in the March meeting. So these techniques are beginning to become kind of really available to groups and to communities of people who don't want to develop them by themselves. Okay, so I'd like to start by giving the first example. Here we're really going to be focusing on measuring density of paramagnetic spins. Paramagnetic spins are non-interacting spins. Each spin is free to do whatever it wants, irrespective of what its neighbor is doing. And what we're interested in, very similar to a magnetic resonance imaging experiment or system, we are interested in the density of spins and where they are. So I'd like to give just a brief background on magnetic resonance imaging. You're familiar with these instruments. I believe we each had our share of sitting in one of these things. They're quite remarkable. They have a spatial resolution of under a millimeter. State-of-the-art instruments have a spatial resolution down to a few microns, maybe 10 micrometers. And the point I want to make is that the collection, the apparatus that collects the signal is basically precession of nuclear spins, are coils. And the coils are sitting about a meter away from the bottom. And if you had this general principle where the distance to your sensor defines the spatial resolution, then here we would have a spatial resolution of a meter. Obviously, these systems have spatial resolution that is not defined by the distance to the sensor. And the question is why? And the reason is that the information is actually encoded in space through transformation to frequency. So you're sitting in a gradient in magnetic field, which means that each position in space defines a different precession frequency of the nuclear spins. And so by collecting all these radiating spins, they're generating RF signals at once, and Fourier transforming, figuring out how much do I have from each frequency, I can basically assign the intensity of each one of these frequencies to a particular location. So this is the power, and what defines the spatial resolution in this case is the strength of the gradient. So in fact, Peter Mansfield, who is one of the Nobel laureates for the MRI, in 2002 he writes kind of a summary, or a summary of the field. There are practical limits imposed by magnetic field strength and imaging time, which currently limit practical resolution to about 1 micrometer. And ostensibly this limit has been reached. So what are the limitations? So one I already mentioned. In a conventional magnetic resonance imaging system, the gradients that you can achieve are about 60 Tesla per meter. This is a remarkable gradient. This is, those of you who know how a 60 Tesla magnet looks like, this is very, very impressive. The second thing, of course, is the sensitivity of the inductive readout. And lastly is this transformation from frequency to space. We really need to know very precisely what the fields are at any given position in space in order to be able to reconstruct our image. So that's something that's called the point spread function. What we have done is to replace or kind of tackle each one of these limitations with our tiny sensor. So one, we're going to use small nanomagnets to generate large radians. Our interest is in mapping paramagnetic spins, not on a body scale, but on a molecular scale, so on a scale of a few nanometers, or a few tens or hundreds of nanometers. And so you'll see that we can generate magnetic field gradients that are far, far greater than 60 Tesla per meter. We're going to replace our readout, the inductive coils, by NV centers. They are themselves the thing that measures magnetic field. And because they are measuring magnetic fields, they will also map for us precisely the gradients in space before we start the measurement, so as to provide a solution for the point spread function. So this is how it works. We have an NV center sitting somewhere in space, and it's going to be stationary, and it's going to sit a few tens of nanometers above the spins that we're interested in imaging. And then we'll bring another tip that has a tiny magnet at its apex, about a 100 nanometer particle of cobalt or nickel. And it turns out that the field gradients generated by this particle on a distance of about 100 nanometer from it are roughly 6 orders of magnitude greater than what you'd find in a conventional MRI system, 10 to the 6 Tesla per meter. And then we're going to send an RF signal that tries to process these spins, and we're going to only collect the signal from those spins that are processing. And the point is that as we're moving our tip, this particular blue slice here is the one that any spin that falls within that slice will process. And so you see that the particular location of our tip, magnet tip, this spin will start processing and will pick up the signal. So as before, the spatial resolution is really limited by the position, by basically how sharp are these resonance slices. Our ability to put this one in resonance and not drive this in resonance, that's what sets the spatial resolution in this problem. And it can reach to below a nanometer, even atomic scale for electron spins. For nuclear spins, a little bit harder because the signals are just very, very weak. So here's an example where we've used this method to really reconstruct in 3 dimensions, full 3-dimensional reconstruction of where spins are, where we're trying to image where are spins inside a diamond matrix. And what you see here, this is the surface of diamond, this blue line, and you see that spins exist only on its surface, and their density is roughly 1 Bohr magneton, 1 spin per nanometer square, and the spatial resolution that is extracted by this method is better than the nanometer. So this is just an example. There are many groups today, we're kind of not interested in pursuing this much further, but who are trying to take these techniques and really push them to the limit where one could then image, let's say, a structure of a protein or something like that. This is a very, very hard problem because the magnetic fields generated by the nuclear spins are 1,000 times weaker than those of electron spins, but nonetheless, it's conceptually a promising approach for looking at really nanoscale paramagnetic spins. All right, the second problem that I'd like to address is the ground state of magnets. Basically magnetization, that would characterize the properties of a magnet. And we all learn from electricity and magnetism, there is a very strong connection, easy connection between magnetism and magnetic field. So we thought this is going to be a really easy problem. We're going to measure some magnetic fields in space, and we're going to know what the magnetization of the magnet is. And we were very surprised, and I'd like to kind of share with you the surprise. Luckily, we were kind of using as a test bed a problem, magnetic textures known as skyrmions. And I'd like to spend kind of 1 minute describing what these are, because it turns out that without the fundamental properties of these skyrmions, we would not have been able to say something intelligent about this system. So skyrmions are magnetic textures. They're somewhere in between a ferromagnet and an antiferromagnet. You see that spins on short length scales want to be aligned, and on longer length scales want to be anti-aligned. It has to do with spin-orbit interaction in the material. One of the interesting things about magnetic textures, if you assume that the magnetization is changing continuously, so there is no discontinuous change in the angle of the spins that are pointing, you all want to have something that's very soft and smooth. It turns out that these textures have a topological property. And to see what that topological property is, one just needs to construct a sphere with unit radius, where each point on the sphere has an angle associated with it. So here, for example, are the angles that have no z component, they're only in the plane. Here is pointing up, here is pointing down. So it's basically just the spherical coordinates, if you like. And you take a texture and you map it onto the sphere, and it turns out you can prove there is a theorem, basically, that says that if the texture, if the magnetization is changing continuously, there are no discontinuous positions, then this texture will map onto either 0 or an integer coverage, or twice or 3 times. The number of times it will cover this sphere is going to be an integer. So it's a topological quantity. And in fact, it's very interesting from an application point of view, because it can store information. And because you can't continuously go from 0 to 1, for example, these things are very stable. All right. But it turns out that there are many textures that actually satisfy this condition. And so the question is, in a given material, what will be the texture? So we wanted to image that. These are some fast qualitative images of magnetization patterns in a disk of 2 micron size of a material known as COFI-B, interfaced with platinum. And you see that at 0 magnetic field, there are some labyrinth kind of textures. These are it looks like a fingerprint, and then as you apply a magnetic field, eventually you form something that looks like a ball, and it looks like a skyrmion, but is it really a skyrmion? What's the magnetization texture here? All right, so we have a magnetic field sensor. We can image above this disk and extract magnetic field. So we're going to basically detect these 2 transitions. So the way an NV center measures magnetic field is by finding what frequency drives the transition from the ground state to one of the excited states. So there are 2 frequencies, and this color map here is the lower frequency as a function of position, and this color map here is the upper transition as a function of position. And by knowing these positions, in fact, one can reconstruct what the magnetic field is along the NV axis, and with lesser sensitivity, one can extract the magnetic field perpendicular to the NV axis. All right, so we have these magnetic fields. Now the question is, what is the magnetization associated with this magnetic field? So here's where we were surprised. Let's suppose I have a very nice magnet that has a uniform magnetization, all spins pointing upwards. Turns out, it is not generating any magnetic field. The reason is that if you think of each one of these dipoles as this tiny current loop, when you put all these current loops together, one next to the other, they all cancel. And the only thing you're left with is a boundary current. So if this film had a boundary, the current, effectively, due to all these dipoles only flowing at the edge, but if this boundary is very, very far away, there are going to be no magnetic fields. So lesson number 1, NV centers do not measure magnetization, because here I clearly have magnetization and my signal is 0. So what are they measuring? Well, let's consider an antiferromagnet. Turns out that for an antiferromagnet, yes, there will be magnetic field signals that we will be able to pick up, but if the distance in which we're scanning is larger than this alternation, it turns out that the signal will be exponentially small. Unlike the paramagnetic spins, where the spatial resolution is given by other parameters than the distance, here, spatial resolution, because these are interacting spins, I cannot flip one electron without doing anything to the others. Here, spatial resolution is in fact limited by the distance. So we have, if we consider general textures of magnetization in Fourier space defined by a length scale or a momentum k, then 0 momentum, the uniform magnetization, produces 0 signal. very large K, like the antiferromagnet, produces a signal that's exponentially small. And if you just draw by hand something that connects these two, you find that it is peaked. And it turns out that it's peaked at a position given by K of equal to 1 over D. Now, the rise here from 0 is linear in K. So this should immediately remind you of something. When you have something that's proportional to K, you know that it's a derivative. So we know that the NV center, in fact, is really sensitive to gradients in magnetic field rather than, gradients in magnetization rather than magnetization itself. So one can do kind of a proper job. I'm not going to derive this for you, just to show that if I have now a bunch of spins, I can collect the signal generated at my NV center from each one of these spins. It's a convolution where this dipolar matrix is basically describing the dipole field associated with each one of these dipoles. And this is the magnetization texture that I'm interested in. And again, if I go to Fourier space, I get a very, very nice relationship where the magnetic field in this Fourier coordinates is given by a product of a matrix that I know, I can easily calculate, and the unknown magnetization. And the whole idea here is to say, well, I'm measuring B, I know D, I can extract M. Easy. When you do it kind of precisely, then first of all you find the prefactor that I mentioned before, this prefactor here, which shows that indeed what you're measuring is a derivative of magnetization. There is a K here. And you see the other coordinates, so this is polar coordinates in Fourier space, K and theta and phi. The problem with this matrix, or the advantage, let's say, is that each one of these rows is linearly related to its neighbor. So if I take row 3 here, here I get just by multiplying by sine phi, and this one I get by multiplying by cosine phi. So there is something peculiar about this matrix which basically says that if I know the magnetic field along one axis in space, this relationship is telling me that I know it in all space. So we're used to thinking of, hey, magnetic fields are vectors, and here I'm telling you it's enough to measure one component of magnetic field above my magnet, and I will be able to reconstruct all 3 components of magnetic field without needing to measure any other quantity, and this is a true statement. To see this, we've taken this one component of magnetic field that we measured, B parallel, and we calculated from it the 3 components in Cartesian coordinates, Bx, By, Bz, out of which we can compute now the magnetic field perpendicular to the NV center, which we also measured. That's what we measured. This is what we calculated based on the parallel component. And note that we're getting a much better behavior than what we could measure. And the reason is that extracting from the NV center magnetic fields perpendicular to its axis is very insensitive because we're sensitive to the B squared, where it's not linearly dependent on magnetic field. Here we get a quantity that's linearly dependent on magnetic field, so we can extract this perpendicular component with much higher signal to noise simply by measuring one component. This is a huge advantage. We basically have a vector magnetometer by measuring one component of magnetic field. But what's the challenge? The challenge is that because all rows are linearly related, the challenge is that this dipolar matrix is singular and cannot be inverted. Which means that there is no way to extract the magnetization from the magnetic field. This is not a mathematical problem. This is a fundamental problem. Turns out that there are infinite magnetization patterns that would produce precisely the same magnetic field. So which one is right? So that's where the topology of these defects comes into play and becomes extremely important. So here's an example. This is our measured magnetic field. And we can basically, by convergence, we can find a magnetization pattern. Here you see that the spins are kind of swirling like a whirlpool. This pattern produces a magnetic field pattern that can match our measurement with arbitrary precision. And you can see here the line fits, which are the model, to the data, which are the dots. The problem with this magnetization pattern, even though it produces precisely our measurement, is that when you map this texture onto the angle sphere, you see that it covers only half the space. Which means that this has a topological charge, how many times it covers the sphere, of a half. And this is not physical. It basically says that this pattern has a discontinuity. And if we say, well, that kind of costs too much energy to have a discontinuity, we can rule out this pattern. But it's only because we have additional input into the problem, we know that these textures must be topological. In contrast, if you look at a different type of texture, this looks like a hedgehog. Here, what you find, again, a very, very good agreement between measurement and this magnetization texture. You see that this one covers the sphere precisely once, and therefore is a very good candidate. Now, obviously, since there are infinite patterns, I can perturb these patterns a little bit, and I'll still get agreement, so it's not a one-to-one correspondence. But the point I wanted to make is that, on one hand, measuring magnetization has the advantage that I need to measure one quantity and I can reconstruct all field in 3 dimensions. The other is that I need additional information about my magnet if I want to really reconstruct magnetization just by measuring magnetic field. All right, so this was interacting spins, but in their ground state. What I'd like to do now is consider a magnet where I have interacting spins, but consider their excitations. So I already mentioned this, some theoretical predictions about spin superfluidity. So I want to spend some time. This paper is from 2014. It's fairly recent, but it turns out that the problem of spin superfluidity is actually very old. It's in fact 50 years old. This is from 1969. So just precisely 50 years ago. This is a seminal paper from Halperin and Hohenberg, Hydrodynamic Theory of Spin Waves, and hydrodynamic is going to appear multiple times in the remainder of this talk. The first sentence of their abstract says, a hydrodynamic theory of spin waves is developed for certain magnetic systems in analogy with the derivation of two-fluid hydrodynamics for liquid helium. So they realized that basically magnets and superfluids have precisely the same description. And the analogy I could point out, in a superfluid, the system has an order parameter, a complex order parameter, and the phase of that complex order parameter is something that is spontaneously selected. It's called spontaneous gauge symmetry breaking. In a certain magnet, like a planar magnet, if there's no anisotropy, the magnetization is going to be in the plane. That's going to be the order parameter. Its phase is going to be spontaneously chosen. And what we know from superfluids and superconductors is that gradients of the phase of the order parameter corresponds to supercurrents. And here the gradient of the phase of the magnetization corresponds to a flow, superfluid flow of spins. So we were intrigued by this relation. We wanted to see, can we probe a quantity that's related to superfluidity associated with this magnetic system? So let me spend just 1 minute giving a few properties of what these excitations are. So we have a magnet, all the spins are pointing in one direction, and the excitations are basically spin waves. So if I tilt one spin, it pushes on the nearby spin, and you can see these kind of correlated spin patterns, but they're moving, they're wiggling in space, and there's a wavelength to this thing. The lowest possible excitation would be an infinitely long wavelength, so all the spins are doing precisely the same thing. That's going to be the ground state. And if there is an anisotropy in the system, or a magnetic field that induces an anisotropy, then the excitation spectrum of this magnet will have a gap, and the gap follows this blue line, magnetic field energy, follows this blue line. The larger magnetic field, there's a bigger gap. And all these spin wave excitations, also called magnons, exist above this gap. So they're filling up the space above here. Or this kind of colored space is what exists above the energy gap. And as I mentioned, in a superfluid, there is a complex order parameter, and there is a relationship, we know for Bose systems, between a density and chemical potential. This is the kind of one of the salient features of a superfluid is that, or a Bose system generally, that if you increase the number of excitations in a Bose system, the chemical potential will increase and increase and increase, but at some point, once it reaches the bottom of excitation, the lowest possible excitation, it's going to be pinned down to this particular value, because from there on, we're going to have macroscopic occupation of this ground state. So chemical potential will cease to increase, very different from a fermionic system, where there, as you increase the number of particles or excitations, the chemical potential will continue to increase because of Pauli exclusion. So here, the chemical potential will rise, and then at some point will hit the bottom of the band and will be pinned. So what do we expect for our magnetic system? Okay, so one, can we use our NV center to measure chemical potential of magnetic spin excitations? And it turns out that the answer is yes, and it's actually rather simple. It basically uses a ratio of two measurements. One is the rate. Okay, so we're going to be looking at relaxation. So before I mentioned that we can probe what frequencies are needed in order to excite from the ground state to the excited state, now we have these magnons, they're spin waves. The way they interact with our sensors, they're basically generating magnetic fields, noise. Right? A uniform magnetic field, we already saw the lowest possible excitation here, the ground state, is one where the magnetization is entirely uniform in space. That is not producing any magnetic fields. But higher frequency excitations will produce magnetic fields, and we're just going to see some noise. And it turns out that what noise does is also generate transitions. And if we look at the rate of transition under two different conditions, one is an equilibrium, where the number of excitations is just set by temperature, and the other is that the rate of transition, when the rate of transition now is set by an enhanced number of excitations, where we pump more of these excitations. I'm not going to say how we pump excitations into the system, but the ratio of these things will define the chemical potential of these spin excitations with no unknowns. So it's a very, very simple, only two measurements, and we get a chemical potential. And this is the result. So what you see here are the chemical potential extracted from this relation as a function of two quantities. One is magnetic field that defines the size of this gap, and the other is the number of excitations generated by some power. And what you see is that the chemical potential indeed rises and then it levels off. For each magnetic field, it rises and then it levels off. And note, it levels off precisely at the bottom of the excitation band. Exactly what you would expect for a Bose system, where the chemical potential will rise continuously and then will get pinned precisely at the bottom of the band where condensation will occur. So here is again a very different kind of application of a magnetic field sensor to measure a quantity that is the chemical potential of spin excitations. All right. Last topic that I'd like to describe in the next 5 minutes or so is hydrodynamic electron flow, basically the behavior of electrons in a metal. And it's a different use of the term hydrodynamic. So before, in the paper that Halperin and Hohenberg were describing, it was also hydrodynamic, associated with superfluidity. Hydrodynamics usually is connected with a conserved quantity. And the type of conservation laws that we had before for superfluids had to do with Goldstone modes, the fact that you have spontaneous symmetry breaking, and therefore you have conservation laws associated with that. The type of hydrodynamics I'd like to talk about now has to do with a approximate conservation, basically, of basically a collection of electrons or particles. So imagine I have a conductor and it has these electrons, and what these stars are, they are impurities. And so as the electrons are propagating through the system, they lose their momentum to impurities or to phonons. Basically, momentum is not conserved. And so this is not a hydrodynamic system. But if you have a very, very clean metal, where the number of impurities or the interaction with phonons is very, very weak, then what the electrons are going to do, they're predominantly going to interact with each other. And so each individual electron is not going to conserve its momentum or energy, but the collection of electrons here do conserve their energy and momentum, and so you have a net conservation of energy and momentum in the center of mass, or the collective property of the system. And this is a property that you're probably familiar with in gases and fluids, because the interaction between molecules is very, very strong, much stronger than any impurities that exist within the gas, and hence we are familiar with phenomenon associated with hydrodynamics in these systems. And I'd like to highlight a few. Just before that, maybe just to mention that this is again a topic that kind of revived itself about 3 years ago and is really exploding with many, many, many materials that are exhibiting this kind of hydrodynamic process. And no, it's not something that's specific to electrons. It's general for any excitation. It could be also hydrodynamics of magnons if the interaction between magnons is strong compared to the loss of energy and momentum of magnons to the lattice, let's say. So it's a very general property of a conserved system. I'm going to skip this because we don't have time. So if I had a channel and I asked, well, what are the consequences of this hydrodynamic, the fact that electrons are strongly interacting with one another and yet not losing their momentum to their environment, one expects a current flow profile in the cross-section of this conductor to be very different from that of a disordered system. In fact, the profile is universal. It's described by a parabola, independent of the dimensions of the system. So we were really interested to try and image this kind of profile and see if it happens. And a natural system to look for it is graphene. And we've done experiments at room temperature. So here, yet another application of how our sensor measures current distributions. You see now the relation again in Fourier space between current density and magnetic field. This time there is a one-to-one correspondence. So if we measure the magnetic field in space, we can know precisely what the current distribution is. There is no unknown, unlike the magnetization case. And we can image it. I'm going to skip this just to show that we can really image it very nicely in 3 dimensions. But more precisely, we'll take a line cut using our scanning sensor, and we're going to compare several different systems. So the red dots is what happens in graphene, and you can see that it follows very, very nicely this Poiseuille flow, this hydrodynamic flow pattern. But we wanted to really be convinced. So we did 2 additional measurements. One is we took very dirty graphene. So you probably know that graphene, if you want high quality, you'd encapsulate it in boron nitride, etc. But if you want it dirty, you just put it directly on silicon oxide. That's how the field started. And you get rather dirty graphene, and you see these yellow dots here. This is a dirty graphene of the same dimension as the red dots here, and you see that the current profile is very, very flat. In fact, spatial resolution here is about 30 nanometers. The silver dots here are a palladium wire. So this is just a regular metal. Again, a lot of impurity scattering in the palladium, and here again you see a very flat profile. So it's quite remarkable that graphene, even at room temperature, is very, very hydrodynamic. And right now we're conducting experiments on many other different materials, especially biosemimetals. There are a lot of materials that have really high mobilities, very long mean free path, where this kind of physics should dominate. All right, so with this I'd like to basically summarize. Hopefully I've kind of motivated you to look for new ways of exploring materials, because I think that this is something that really requires continuous innovation to figure out new approaches to poke into materials and be able to look at phenomena in different ways. And here I'm just highlighting some of the people that have contributed to the various topics that I've talked about today. Thank you.
Questions? Yeah.
The previous slide, your parabola prediction data has any difference?
Right. So you see, error bars are not so tiny. So you might ask, well, okay, is this really a dip or is it flat? We're not sure yet. So we've seen this kind of double hump in many samples that we've scanned, but if you look at palladium, it also has a dip in the middle here, whereas the dirty graphene doesn't. So it's something that I think we really need to improve our signal to noise in order to be able to say more precisely whether there is a dip or not. There are some good reasons to expect a dip in this system, but I'm not convinced that we're seeing it. So at this point, I'd say, don't know.
What happened to the dimension? Did you try to measure the different dimensions?
Yes. So if you increase, so what happens as in a, in air flowing over a surface, there's a boundary layer. This precise Poiseuille flow occurs when the boundary layer is basically larger or comparable to the channel width. If the channel width is large compared to this boundary layer, then what you'll find is you'll find it increase over some finite dimension and then it'll flatten out. And you see that very nicely.
A naive question. There's one-to-one correspondence of the current with the measured response that you have here.
Yeah.
Is that at least formally true, assuming arbitrary resolution in 3-dimension as well? Does that rely on the fact that I have 2-dimensional flow, or
Yeah.
in principle can I? So
It does. So if you have a 2-dimensional electron flow, currents in the plane, I could describe them in terms of a magnetization whose direction is always in the z direction, always perpendicular. Only the magnitude of the magnetization changes. So if I know that my magnetization is a scalar, it has only a magnitude and no direction, I can reconstruct it. If I have currents flowing in a 3-dimensional slab and they're flowing up and down in all different directions, this no longer holds, and the problem becomes again intractable.
Is it correct to say that despite the degeneracy of your dipolar matrix, you can still reconstruct the topological number of the texture?
Yes, definitely you can. Well, I wouldn't say you can construct because, we haven't tried, for example, to generate a magnetization pattern that has a topological number of 2. I'm pretty sure we should be able to do it and have a pattern that agrees very nicely with our measurement. So I can tell you that it's not 0, but I don't know if I can tell you if it's 1 or 2. We suspect it's 1. That's what other people believe. It's harder to get a higher topological number, but yeah, it's really a limitation that does not allow you to say too much about magnetization by measuring magnetic field. Very sad.
Did you try on the mercury electron?
We have not tried to image on mercury. But we're imaging now tungstenite telluride, which should have similar properties to the mercury telluride quantum wells in terms of. Right now we're in thick layers because that's where mobilities are really, really high and you can very nicely see hydrodynamic behavior. It would be very nice to see what happens in monolayer where there you have Ormston Hall effect, etc.
Any more questions, comments, tomatoes? I need to say something. Okay, so let's thank Amir.